Okay, this is Stokes Theorem. We are rapidly coming towards the end. This is the last topic of the course. So thank you for sticking it out to the very end. All right, so Stokes Theorem, right? We have S is an oriented surface with a unit normal vector n bounded by a piecewise smooth curve C oriented counterclockwise on the side with positive n, right? So in other words, just use your right-hand rule. If you curl your fingers in the direction of C, your thumb should roughly point in the direction of n, the normal vector, right? So if F is a C1 vector field, so M, N, and P have continuous first partial derivatives on an open region containing the surface, right? So we imagine this surface is sitting in space, right? So we have some region Q that encloses that surface, as well as the curve, of course, right? So we can calculate the line integral of the vector field F dot dr, right, over that closed curve. And so you'll see some books put a little loop through the integral here, indicating that it is a closed curve C, right? We can calculate that line integral either directly, right, or we can calculate it as the surface integral, right, or the flux integral in this case, of the vector field, which is the curl of F dot n ds, right? So, right, as with the divergence theorem, right, rather than calculate this directly, it's usually easier to calculate the flux integral, the higher dimensional version, right? Because in the divergence theorem we had, right, the surface integral. It was a closed surface, right? And we were calculating the flux integral. Instead, we were calculating the volume integral that was enclosed, but we had to take the divergence first, right? So that's a reminder of the divergence theorem. And this is Stokes theorem. Right. So before we do some examples, I should just kind of say that the divergence theorem and the Stokes theorem, Green's theorem, as well as the fundamental theorem of calculus, these are all really the same thing. You know, some use the curl, some use the divergence, but they're all just derivatives, right? And so the most general form of Stokes theorem really just has, right, the integral over the boundary of the surface, right? In this case, the curve C is the boundary. So this little symbol means the boundary. I'll use M for surface here. Of some differential form, right, I'll call it omega, can be calculated as the integral over the surface itself, but you have to take the derivative of that form. So this is sort of a very abstract, generalized version of what's called Stokes theorem. But, right, this essentially encapsulates all of Stokes theorem, the divergence theorem, as well as Green's theorem, and even the fundamental theorem of calculus, right? But we're not going to worry about that version of Stokes theorem. That's for a more advanced course. Yeah, so in this course we'll do some examples where we calculate the line integral, and we also calculate the surface integral, and we effectively show that we get the same thing here. All right, so let's do that. Okay, so here's our first example. We have a vector field F. It's zi plus 2xj plus x squared minus y squared k. The surface S is the plane z equals 6 minus 3x minus 2y in the first octant. Yeah, the first octant, I don't know if we've talked about that, is basically where x, y, and z are all positive. So x is positive, y is positive, positive greater than 0, and z is positive. Right? So it's similar to the first quadrant, right, in 2 dimensions, So because there's 8 octants in 3 dimensions, we just call it the first octant, right? And C is the boundary of this portion of the plane, right? Right. So what are we talking about here, right? So let's graph. Let me see if I can graph it this way. Here's the y-axis. It's got to be a little bit bigger here. Okay, so here's the y-axis. Here's the x-axis. And here's the z-axis, right? So when x and y are 0, z is 1, 2, 3, 4, 5, 6. When z and y are 0, x is going to be 2. And when x and z are 0, y is going to be 3, I think. Right. So the plane, right, it's really 3x plus 2y plus z minus 6 equals 0. So in that form, you can see that, right, when x and y are 0, z is 6. When x and z are 0, y is 3. And when y and z are 0, x is 2. So we're talking about this portion of the plane. Oh, these are supposed to be straight. Draw a straight line there. All right. Right, so that's the portion of the plane in the first octant. And now we can see what C is, right? C is just this triangle oriented which way? So if the thumb is pointing out at us, then we're going counterclockwise this way, right? So that's my C. And S is just this piece of the plane, this, you know. Okay, so that's S. All right, so we want to calculate this line integral. And of course, to do that, because it's, right, this is not a piecewise, this is not a smooth curve, it's a piecewise smooth curve. It is 3 pieces, right? You have this line segment here, this line segment here, and this line segment here. So all 3 pieces are straight lines. I know it doesn't look straight, but it, you know, that's my sloppiness, right? So sorry about that. But they're all just straight lines. So to calculate this line integral, we'll just divide this up into 3 lines. I'll call them C1, C2, and C3. Right. So again, this goes back a few sections when we learned how to calculate line integrals. And we did one like this. Where we just had to add up the 3 line integrals, one for each piece, right? Okay, so we have to parameterize each piece, right? Let's do it separately here. So C1 effectively goes from the point 2, 0, 0, 2, 0, 0 to the point 0, 3, 0, right? And if it helps, you can just graph it in the xy plane. Right. So this is our C1 here. I'll put it in yellow as it should be. Right. Okay, so C1, right? We'll just call it R1 of t. So we're starting at 2, and we're ending at 0. So why don't we do 2 minus 2t? If t starts at 0 and ends at 1, I think that works. And then y just goes from 0 to 3, so we can do 3t. And t goes from 0 to 1, right? So that's the first piece, right? The second, I'll call it R2. So now we're starting at 0, 3, 0, and we're ending at the point 0, 0, 6. Oh, so I forgot something very important here. This is right, so this line C1, this line here is only in the xy plane, but of course overall it's in space, so I have to indicate that that the z coordinate here, the z component rather, is just 0. So let me put that in here. Right. Yep, so same thing for R2. Right, since this takes place in the yz plane, we know x is 0. And let's see, y is going from 3 to 0. So, yeah, so how about, I don't know, so t is starting at 1 here, right? And we want to end at 2. So let's see if I can just guess this right here. This is going to be 6 minus 3t. If t is 1, you're at 3, and if t is 2, you're at 0. So I think that's right. And then z just goes from 0 to 6. So 6 times t. Oh wait, that goes from 6 to 12. So 6 times t minus 1, right? So yeah, 6t minus 6. Sorry, 6 times t minus 6. All right, I think that works. Yeah, okay. And finally, C3 is the line segment from 0, 0, 6 to 2, 0, 0. So this takes place entirely in the xz plane, so y is going to be 0. And we want t to go from 2 to 3. Well, all right, so z is going from 6 to 0. So when t is 2, we want to get 6. So that would be 3 times t would be 6, right? But it's going backwards, right? So we want minus 3t. So let's see, is it 9 minus 6t? So when t is 3, we're at negative 18. That's not going to work. Yeah, from 6 to 0. So 24 minus 6t. When t is, oh, I'm sorry, we're starting at t equals 2. So yeah, 12 minus 6t. I think that's all we need. 12 minus 6t. I said it, but yeah. All right, so let's check. When t is 2, oh, we're at 0. When t is 3, we're at negative 6. Okay, so it has to be 18 minus 6t. 18 minus 12 is 6, and 18 minus 18 is 0. Right, I was going to get it eventually, right? X is going from 0 to 2, so that's just 2 times t minus 2, so 2 times t minus 4. So when t is 2, we're at 0, x is 0, and when t is 3, 6 minus 4 is 2. All right, I think we got it. I just want to check one last time to make sure these are all correct. Yep, okay, I think that's it. Okay, so now we just have to calculate the line integral. Remember, this is our vector field up here. So I'm just going to copy this down here so we can use it. Yeah, so let's just start with C1 and do the line integral. Right? So here's f, and here's, so dr is just going to be negative 2, 3, 0. And z in this case is, well, 0. 2x is going to be 4 minus 4t. Right, and x squared minus y squared, oh, that, so here's x squared minus y squared. Right. All right, and then dr is going to be negative 2, 3, 0. Right. And t just runs from 0 to 1. So, yeah, so this is a definite integral from 0 to 1. I'll leave the C1 as this is the first curve, right? So when we take the dot product, all of this isn't going to matter because it's just multiplied by 0. So it's the definite integral from 0 to 1 of 0 times negative 2 plus 3 times 4 minus 4t, right? And I got that from the 2x. So I think it's just going to be 12 minus 12t dt. Okay, so when you integrate that, you get 12t minus 6t squared. From 0 to 1, it looks like 12 minus 6, which is 6. Right, again, that's not the answer. That's just for, this is for C1. Right, now let's do C2. Right, so we're going, t goes from 1 to 2, and C2. So z is going to be 6t minus 6. 2 times x, well, that's just 2 times 0, which is 0. And then x squared minus y squared. So this is going to get a little bit crazy here. X squared is 0. Y squared is 6 minus 3t quantity squared. And now we need the dot product with 0, negative 3, and 6 dt. Yep, this one's not quite as easy as the other. So this is just going to be negative 6 times, so I'm trying to, so I'll pull out the negative 6, and then we can pull out a 3 as well. In fact, 3 squared is 9. So negative 6 times 9 is negative 54, right? And then we're just going to get 2 minus t squared, right? So this becomes 2 minus t squared, right? So we pulled out the negative 3 squared. I multiplied that by 6 for the dot product, and I think that's what we get, right? So t squared minus 4t plus 4 dt. So the integral of that is 1/3 t cubed minus 2t squared plus 4 times t. And then we got to plug in the 1 and the 2. And then still multiply by negative 54. Right. So when we plug in 2, we get 8 over 3 minus 8 plus 8. So that's just 8 over 3. And when you plug in 1, you get 1/3 minus 2 plus 4. So 2 plus 1/3 is 8 over 3. Wait, 2 1/3, I'm sorry, 7 over 3. 7 over 3. Right? Yes. Okay, so yeah, so that's just 1/3. So this is going to be negative 54 over 3, which is negative 18. I think I can squeeze it in here, right? Okay, negative 18. And again, that's only for C2, right? So this is for C2. And then finally for C3, I think I have just enough space to cram that in at the bottom here. So t goes from 2 to 3. This is for C3. Z is going to be, you know what, I have a little bit more space here. 2 to 3, this is C3. All right, so Z is 18 minus 6 times t. 2 times x is going to be 4t minus 8. And then x squared minus y squared. So x squared is going to be, well, 2 squared, which is 4, times t minus 2 squared. And we'll unravel that later. And then dr is going to be 2, 0, negative 6 times dt. Yeah, so this is not going to be that pleasant either. Let me make sure. So z squared. Sorry, there's no z squared. It's just z. This is z here. And then 2x. Yep, 4t minus 8. And then x squared minus y squared. So y squared is 0, of course. And x squared is just, well, 2t minus 4, the quantity squared. So when you factor out the 2 squared, you get 4, and then t minus 2 squared. So I think that's it. Okay, so to take the dot product, we're going to get 2 times 18 minus 6t. So 2 times 18 is 36, minus 12t. And then the middle term here, 4t minus 8 times 0 is 0. And then we're going to get negative 6 times 4, which is negative 24, times t squared minus 4t plus 4. Okay, so before we integrate this, let's work this all out. We're going to get negative 24t squared, and that's the only squared term we have. We're going to get negative 24 times negative 4, 96 times t, minus 12 times t, right? So 96 minus 12, I think we get 84 times t. And then negative 24 times 4 is negative 96, plus 36 is negative 60 dt. All right, now we can integrate this. This is going to be negative 8t cubed plus 42t squared minus 60 times t, and then evaluated between 2 and 3. So plugging in the 3, we're going to get 27 times 8, 216, but it's negative, so negative 216. And then 42 times 9, 33. Wait, sorry, 42 times 9 is 378. Got to hit the right buttons on my calculator here. And then negative 60 times 3 is negative 180. All right. And then minus, when you plug in 2, now you're going to get 2 cubed is 8. 8 times negative 8 is negative 64. And then 2 squared is 4. 42 times 4 is 168. So 1. And then minus 120. So we get some pretty big numbers here. 260 minus 180. So this is negative 18 minus 20 minus 64 minus negative 16. So this ends up just being 16 minus 18, which is just negative 2. Wow, okay. So I hope this is correct. And now we just have to add the 3 integrals up here. So 6 minus 18 minus 2, I think in that order. Right. So negative 14. All right. I hope that's it. Again, could have easily made a mistake here, but that should be the line integral, right? All right, now let's calculate the surface integral. Okay, and it should be the same, right? According to Stokes' theorem, they should be equal. That's what it says. All right, so yeah, let's just work that out. All right, so this is the surface integral of the curl of f, so we'll have to calculate the curl of f, and then dot nds. Okay, so the curl of f, just do our determinant, I, j, k, the x partial, the y partial, the z partial, and then f is z 2x, x squared minus y squared. All right, so the first component is just negative 2y. The second component is 1 minus 2x. And the third component is 2. Right? The derivative of 2x is 2. So I think that's it. Yep, 1 minus 2x. All right. So that's the curl. And then what's n? So n, of course, is the unit normal vector. Or, rather than do the unit normal vector, remember, we can calculate this as the curl of f, right, dot Ru cross Rv. If we parameterize the surface, and then du dv. Okay, so how do we parameterize this surface here, right? So this is a plane, right? And here's the plane. It's just z equals 6 minus 3x minus 2y. So yeah, z equals 6 minus 3x minus 2y. Yep, just making sure. Right, so yeah, we can parameterize this. I would just use u as x, v as y, right? Or, yeah, maybe instead of doing that, why don't we just do it the old-fashioned way? This is a surface. It's already solved for z. So the x partial of g is just negative 3. The y partial of g is just negative 2, right? And n is pointing upward slightly, but it is pointing upward. So that means that our n is just going to be negative gx, so that's going to be positive 3, positive 2, and then positive 1. Okay, so yeah, I mean, we can parameterize it, but we're just going to end up with the exact same thing, right? So, okay, so the curl of f, we already have that, negative 2y, 1 minus 2x, and then 2. And then dot product with our n here is just going to be 3, 2, 1. And then this will just be dy dx, right? Yeah. So we'll get the bounds in just a sec. Well, let's get the bounds right now, right? So yeah, so here's our R, here's our region. It's just this little triangle here, right? So y is just going to be 3 minus 3 over 2, right? 3 over 2x. Right, so that's just this line, this little line segment right here. So let's write that down. Y is just going to be 3 minus 3 over 2 times x. Right. In other words, right, y just goes from 0 to 3 minus 3 over 2 times x. And x just goes from 0 to 2. Yeah, 0 to 2. Okay. So y goes from 0 to 3 minus 3 over 2x, and then x goes from 0 to 2. Vertically simple region, right? Okay, so the dot product then is going to be negative 6y plus 2 minus 4x plus 2. So that's the integrand. That's what we're going to integrate here. And yeah, So let's just clean this up for a minute. So we're going to get 4 minus 4x minus 6y. So we'll do the first integral with respect to y. And when we do that, we get 4y minus 4xy minus 3y squared. And we're just plugging in this right here. Right? Yeah. So 4 times 3 minus 3 over 2x minus 4x times 3 minus 3 over 2x, and then minus 3 times, 3 minus 3 over 2x squared. All right. So at this point, this is just a single definite integral. I'm just going to throw this in the calculator because honestly, I probably don't have enough space to work it out. And yeah, at this point, feel free to just use your calculator. Okay, so I did multiply this out a little bit. I just didn't want to waste all that time here. So you expand this out, and this is the integrand. When you integrate it, you get this. And then when you plug in the 2, you get negative 2 plus 18 minus 30, which I do believe is negative 14. And that should be no surprise because that's the answer we got by doing the line integral directly. Okay. So, yep, they're both equal to negative 14, as guaranteed by Stokes' theorem. All right, so you can see that neither one of these was altogether all that simple. We did the line integral. We had to split it up into 3 separate line integrals, and so that was a bit of a nuisance. And then we did the surface integral, or the flux integral, rather. And that was also a little bit of a nuisance, although I still prefer that over the 3 separate line integrals. But it's nice to know you do get the same answer, negative 14, either way. And so that's Stokes' theorem, right? Stokes' theorem is going to guarantee that, well, again, as long as this vector field is, has continuous partial derivatives, right? And, the surface is, oriented surface, of course, with a piecewise smooth boundary, then the line integral will equal the flux integral. Okay, so that's our first example. Let's do another one. Okay, so here's our vector field, xy times I minus z times j plus y times k. And the surface S is, well, this is a paraboloid. Z equals 1 minus x squared minus y squared, right? So it's going to be upside down, but it's for z greater than or equal to 0. Okay, so here's the, oops, we got to go equal in all directions here. All right. So the surface is just a paraboloid. So here's 1 and negative 1, 1 and negative 1, and then z equals 1 as well. And that's looking a little like a sphere. Yeah. Okay. Remember, not a sphere, right? It's a paraboloid. Right. Yeah. So something like this. Right. So what's the boundary? Remember, this is an open surface, right? It does not include the xy plane. Right? So the boundary is just this circle here. Let me try that again, right? Yeah, it's the unit circle, radius 1. Right. How do I know it's radius 1? Well, when you have the surface is 1 minus x squared minus y squared, when z is 0, then you just get x squared plus y squared equals 1, which is the unit circle, right? S1. This is the symbol for the unit circle. I'll just call it unit circle. Right. So, yes, when you get far enough in math, we're going to use the symbol S1 for the unit circle, right? S2 would be the two-dimensional version for that. That would be the sphere. And then S3 would be, well, a three-dimensional sphere, which is very difficult to visualize because we don't have 4 dimensions. Okay, so S1 unit circle, right? So that's C. So this is C here, right? And it looks like if we're going to use the upward normal vector this way, right? So these are our ends. That means that we're going around counterclockwise, right, around the circle. Right. Again, it might help if I draw it like this. So here's the red circle. Right. And if we curl our fingers on our right hand counterclockwise like this, our thumb will be pointing, well, at us, right, directly up in the z direction, right? So, right, it's only at the North Pole that you get, you know, a vector pointing directly upwards, a normal vector pointing directly upwards, but they all have some vertical component, right? None of them are pointing downwards, unless you're on the inside of the surface. And if you're on the inside, then you have the opposite orientation. Okay, so we want to evaluate the line integral of that vector field over this circle, right? And it doesn't tell us how we have to do it. We can use Stokes Theorem. And if we use Stokes Theorem, that means we're doing the surface integral over the surface S, right, of the curl of F, right, dot n, dot product with n ds. Right, so let me erase the C here. And I can put in more space. All right, sorry about that. There we go. Just to emphasize that that's the dot product. All right, curl of F. That's the easy part here. We all know how to take the curl. I'll do the determinant version. These are partial derivatives, and then this is xy, negative z, and then y. So let's see, the x component will just be the partial of y with respect to y is 1 minus, well, the partial of negative z is negative 1. So minus negative 1 is 1 plus 1. And then, yep, that's the z partial. And then the y component will be 0 minus 0, which is 0. And then the z component will be 0 minus x, so negative x. So, yep, just 2, 0, negative x. Okay. Right. And what's our normal vector? Well, remember, this is going to be a surface, g of xy. It's 1 minus x squared minus y squared. So the x partial of g is negative 2x. The y partial is negative 2y. And so our n will just be 2x, 2y, and then 1, right? Yep, so to do the surface integral, well, we'll fill in the bounds in just a second. We're going to take the dot product of 2, 0, negative x, and 2x, 2y, and then 1. Isn't that right? And then we'll do dy dx, of course. Right, so 4x plus 0 minus x. So it looks like we're just integrating 3x. dy dx. Okay. Right. Okay, so the region R, of course, is just the unit disk, right? So we're going from negative square root of 1 minus x squared to positive square root of 1 minus x squared. X just goes from negative 1 to 1. But this does not look pleasant, right? So why don't we just switch to polar coordinates? 0 to 2 pi, because we're going all the way around the circle. And r just goes from 0 to 1. So 3 times x is r cosine theta. And dy dx is r dr d theta. Don't forget the r, right? This is our dA in polar coordinates. A lot of people forget the r. You have to be careful of that. Yep, so we're doing 0 to 2 pi. I'll bring the 3 outside. This is just cosine theta d theta times the integral from 0 to 1 of r squared dr. And let's do this one first because I think you recognize this has to be 0 because, you know, for cosine from 0 to 2 pi, right, you just get 0. So whatever this is, this obviously is just 1/3, right? But you get 0. So a lot of work to show that this line integral is 0, right, by Stokes' theorem. Got it? Right. Okay. So, yeah, we didn't evaluate the line integral directly because we didn't have to. We can use Stokes' theorem. There's no problem with that. But you'll see that it's actually just as easy. In fact, I think it's probably even easier given that the curve, right, this is our C here. It's just a unit circle. And you know how to parameterize the unit circle, right? It's just going to be r of t, right, cosine and sine. And t will go from 0 to 2 pi. Right, and so dr, we'll need the dr for this too. This will be negative sine of t, cosine of t, right? And the vector field f, so I should copy that down. There it is. So let's calculate the line integral directly. Of course, I keep forgetting that this is a circle in the xy plane, but because the vector field is in space, let's put the circle in space as well. So the z component, of course, will be 0 as it's just a circle in the xy plane, right? Okay. Right, so the vector field is just xy. Here x is cosine, y is sine. And then negative z, well, z is 0, so this is negative 0, which is 0. And then y is going to be sine of t. Right. And then dr, we already mentioned, is negative sine t, cosine t, and then 0, dt. Oops, we got to integrate, of course. Oh, t just goes from 0 to 2 pi. We already said that. All right, so we still have to do the integral from 0 to 2 pi. Dot product will just be negative sine squared times cosine plus 0 times cosine plus 0 times sine. So that's it. It's just negative sine squared times cosine. So easiest way, in my opinion, is just to do a substitution. U is just sine, du is cosine. And we'll bring out the negative here. Yeah, that's right. So this is going to be integral of u squared du, where sine of 0 is 0. Sine of 2 pi is also 0. So because you're integrating from 0 to 0, we get 0. Right. So that's the value of the line integral. But we already knew that, right? We did it by calculating the flux integral. And as you can see, doing the line integral directly actually was easier, considerably easier, than doing the flux integral. But again, Stokes' theorem guarantees the answer is the same. They're both 0 here. Okay, I don't know why I put another equal sign there. just equals, right? So yeah, you know, in the last problem, we could say for sure that the flux integral was probably easier than doing the line integral. What made the line integral probably easier here is that it's not piecewise, right? It's just one continuous smooth curve. It's a circle, right? It's one piece, right? Whereas the surface, we had to do the dome here, this little paraboloid here, upside down paraboloid, right? But even that wasn't necessary, right? The key is that we're evaluating the line integral over the disk here, right? C is the disk. It doesn't matter what surface you're talking about, right? Right? This surface here could have been just a weird bubble shaped, right? It could have been something like this, right? Which would have made it much more complicated. Or you can just smash it all the way down and just make it, well, the unit disk. Right? So it didn't have to be this paraboloid here. It could have just been the disk. Right? And if you're gonna do the disk, right, it just becomes much easier. So let's do the double integral again, but this time using S as just the disk of radius 1. And you'll see it's considerably easier here. Okay, so we already did the curl of f. The curl of f was 2, 0, negative x. Oops, double integral, right? 2, 0, negative x. And now what's n? Well, n is coming right out at us, right? If this is the disk, n is pointing upward. And remember, we're going counterclockwise, so n has to point upward. So it's just k, right? 0, 0, 1. Oops. 0, 0, 1. ds. Well, in this case, ds is just dy dx, right? And so this is just the iterated integral of 0 plus 0 minus x. So negative x dy dx. And again, we might as well convert to polar coordinates here. Right? So 0 to 1 and 0 to 2 pi. But yep, once again we get the integral from 0 to 2 pi of cosine theta, which of course is 0. So it doesn't matter what the r integral was. Right? It's going to be negative 1/2, but it doesn't matter. 0 times negative 1/2 is still 0. So that would have saved us a lot of work. Well, a little bit of work with the parametrizing the surface here, the paraboloid. But yeah, it turns out it didn't matter either way. Any way you do this, you're going to get 0. Right? Right. So what does that mean physically, right? Well, in terms of the flux integral, it just means that, right, the vector field points, just as much outward as it does inward. And so the outward and the inward end up canceling. I think that's what happens. Or it's possible that all the vector field here is going to be tangents to the surface, in which case the dot product with the normal vector would be 0. Right? So if the vector points outward, perpendicular to the surface, and all the vector fields here are tangent to the surface, then the dot products will always be 0. I don't think that's what happens here. My guess is that the vector field is not going to be tangent to the paraboloid. That some of the vectors will be pointing outward, some will be pointing inward, and then they just cancel out. You get 0 in the end. Right? And in terms of the line integral, it just means that, right, so the vector field probably does point perpendicular in all directions here. So yeah, z is 0. You know what? I don't think that's the case. But again, so I think what happens is some of the vectors point this way, some of the vectors point this way, and right, the dot product ends up sort of canceling in the end. Right. Well, those both point outward, right? Some of them point inward. So some of them might point inward, some of them might point outward. And over the entire curve, right, the line integral takes the sum of all those over the curve. You just get 0. So, right. So another good example. All right, last example. Right, you have a vector field f. It's just z squared, x squared, y squared, right? And the surface is going to be a cylinder z equals y squared over the square of length and width a. So a is just a constant here, right? So a is a constant, right? It's just the size of the square. Oops. Oh, sorry about that. Okay, so yeah, so this is, what is this going to look like here? This is going to be pretty tricky to graph, so I'm going to do my best. So here's the z-axis. I'm going to make this the y-axis, and this will be the x-axis. And let's make this a, and this is also a, right? So a 0, 0 for x, 0, a 0 for y, and then this is just the square in the xy plane, right? Right. But the surface now is going to look like this, right? So z equals y squared, right? So when x is 0, z is 0, or when y is 0, z is 0, and when y is a, z is a squared. So let's make this a squared, right? So 0, 0, a squared. So this is the projection of the parabolic cylinder against the yz plane, right? But it extends this way too, and this is also the cylinder, right? So this is the surface, this is the cylinder, right? And so you can see that the yellow here, that's the bounding curve, that's C. So we're going counterclockwise, as usual. This is C. And again, I want to, highlight the surface here, but I'm going to do it in a very dark blue color here. Let's see, is that dark enough? Yep. Okay. So we want to evaluate this line integral, right? So we could do it directly, but that would involve parametrizing each of these 4 curves, right? So C1, C2, C3, C4, right? C1 and C3 are just straight lines, so that's not hard. But C1 and C2 are parabolas. No, that's fine too, right? Y equals x squared, or whatever it is. In this case, it's z equals y squared, right? So because it's 4 separate curves, and I'd rather not calculate 4 separate line integrals here. Yeah. Right. Let's just use Stokes Theorem and calculate the surface integral of the curl of f, the curl of f, right, dot n, right, the flux integral. Okay, so n is going to be pointing like this, right, but mostly with a vertical component, so none of them are going to be pointing downward, right? Use your right hand rule here. So these are our normal vectors, right? They'll be pointing upward. And, yep, so we'll just use the usual negative gx, negative gy, and 1. So g, of course, is just y squared. So the x partial is 0, and the y partial is 2y. So the normal vector n has components 0, negative 2y, and 1. Right. And now for the curl of f. Yeah, okay, I got to squeeze it in somewhere here. Let me do it way down here. So another determinant, I, j, and k. And these are the partials, partial derivatives. And then the components of f are just z squared, x squared, y squared. So the first component will just be 2y minus 0. The second component will be 2z minus 0. The third component will be 2x minus 0. So 2y, 2z, 2x. Okay. 2y, 2z, 2x. Dot product with n is just 0, negative 2y, and 1. This will be dy dx. And over the region R, of course, is just the square here. It's just this red square in the xy plane, right? So, yep, so x is going from 0 to a, y is going from 0 to a. Right? Yeah, it's a square. There's no need to convert to polar coordinates here, right? Yep, so we have an integral from 0 to a, another integral from 0 to a, iterated integral. And the dot product is going to be 0 minus 4yz plus 2x. Okay. Again, there's a bit of an issue here. We can't integrate this directly because there's no z. It's just dy dx. So what was z? Well, z was defined as the cylinder, right? Z equals y squared. So, yep, we have to plug that in here. Z is really just y squared. So when we do that, we get negative 4y cubed plus 2x dy dx. All right, first integral, not too bad. It's going to be negative y to the fourth, right? Y to the power 4 plus x squared, evaluated between y equals a and y equals 0, dx. So negative a to the fourth plus 0 to the fourth, right, plus x squared. Oh, I'm sorry. I don't know where I'm getting the x squared from. It's still 2x. Boy, I really botched that, didn't I? Right? It's not x squared yet. We're integrating with respect to y, so this is 2xy. All right. Apologies. That's very sloppy there. All right, so negative a to the fourth plus 2xa, or 2ax dx. Now we integrate with respect to x. Oops. So negative a to the fourth times x plus a times x squared, evaluated between 0 and a. So we're going to get negative a to the fourth times a plus a times a squared, and then minus 0. So negative a to the fifth plus a cubed, or a cubed minus a to the fifth. That's supposed to be a 5. That's a little better. So I think that's the answer. Yep, a cubed minus a to the fifth, right? So that's the value of the line integral by Stokes' theorem. Right. So we didn't calculate it directly. We used Stokes' theorem and calculated the flux integral of the curl of the vector field. Right. Again, don't forget to take the curl, because, right, if you integrate the vector field f dot n, you're not going to get the same answer for the line integral. Right. So remember, with Stokes' theorem, right, if you're doing the flux integral, the surface integral, you got to take the curl of that vector field first. Right? Because, yeah, if we had used this vector field here rather than the curl, well, you're not going to get the right answer. Right? You're not going to get this. Again, it's as if you want a challenge, then right, do it the long way. Do each of these 4, line integrals over each piece of the curve here. You know, each piece is probably pretty easy, but putting all 4 of them together is, well, not entirely pleasant. It's a lot of work. So I think this is a case where doing the flux integral was easier than trying to do all 4 of these separately. But I haven't tried it, so I don't know for sure. All right, I think 3 good examples. You know, and there's, you know, a few more in the homework you can try. And that's it. Thank you very much. It's been a pleasure. This is really one of, you know, it's just an awesome course. You know, very much things that you're going to use over and over again in physics, engineering, electromagnetism, fluid dynamics, all sorts of fields. Just very useful. Or if you're a mathematician, you should love this also, because this, you know, things like Stokes Theorem in its generalized form, talking about differentiable manifolds and differential geometry, this is just the beginning of that, right? And you can extend this to surfaces, not just in 2 dimensions or 3 dimensions, but as many dimensions as you want. And it's all fascinating stuff. But this is where our story ends. And so thanks again, and best of luck on your exams. And I hope to see you again soon.